We are back to calculus of variations after discussing how to formulate the mechanics problems and structural design problems using calculus of variations. We are now looking at calculus of variations again in order to see how we can solve the equations. In the case of the structural design of a bar and a beam, we discussed how we can solve analytically sometimes, and we also saw how to solve numerically when we cannot solve analytically. Now, let us come back to calculus of variations or go back to calculus of variations to see after we write Euler Lagrange equations how we can solve them, And there are some standard techniques to solve, and one of them is to do with invariants that exists in Euler Lagrange equations when you change variables or when you express the variables that you have in terms of parametric form or some other variables, and a way of integrating Euler Lagrange equations. Euler Lagrange equations, as we know, are differential equations. When we say we solve differential equations, we essentially mean that we are able to integrate them either analytically or numerically. In this lecture, we will discuss a few methods that enable us to do this analytically, which is what we call integrals and invariants of Euler Lagrange equations. Let us get on with this topic. So, here is the outline of the lecture. First, we discuss what are called the first integrals of Euler Lagrange equations. They are called first integrals because when you have Euler Lagrange equations which are differential equations, if it is a dynamic system that we have considered for which you have written Euler Lagrange equations, usually there will be second order differential equations in terms of time. Now, when you say first integral, you will get one order reduced, right. That is why it is called first integral. There is an interesting theorem after M.E. Noether's, or what is called a Noether's integral. We will discuss that also, and then we will see what happens to EL equations. By EL we mean Euler Lagrange equations when we use parametric form. When you have two variables x and y, you can express both of them in terms of another variable, let us say t, x of t, y of t. Then what happens to Euler Lagrange equations? Likewise, when do Euler Lagrange equations remain invariant? That is, you change to parametric form or change of variables, and still Euler Lagrange equation should be the same form, they should be of the same form. So, what we will learn in this lecture is how to simplify the Euler Lagrange equations so that it will be easy to solve analytically sometimes, and numerically definitely easier than doing without this so called first integrals. And we also discuss how to take advantage of the parametric form and other change of variables to solve calculus of variations problems. So, it is more than formulating equations, that is what this lecture is about. We know given a calculus variation problem, we can write equations now, Euler Lagrange equations, they are differential equations, and then the boundary conditions also. Now, we go a little bit beyond that. And just to recap what we have discussed in calculus of variations, we have discussed these multiple derivatives and multiple functions, 2 and 3 independent variables, equality and inequality constraints, variable end conditions, and at the end we also discussed broken extremals, so called Weierstrass-Erdmann corner conditions. We discussed all of these. Now, we are putting them to use in mechanics and structural design, but this topic is there as to how to solve these. So, there are a few concepts that we need to understand to do this first integrals or invariants. Okay. After doing this, let us be warned that we will still not get a solution, but we will arrive at equations that are simpler or easier to solve. Okay. That is something that whatever we discuss in this lecture does not enable you to solve any problem, but it will give you a method to simplify the equations under certain conditions, not always. Let us consider the Brachistochrone problem itself to see whether we can solve the problem that is given there. Okay. That is our calculus of variations problem, minimizing the time that this bead will take to come from point A to point B under the influence of gravity. So, this is the problem, and Euler-Lagrange equations, if I write in this case one equation, because we have only one function y of x, we have one differential equation in y. This is differential equation, sometimes we just write it as dE. Looking at this equation, it has y, it has y prime square here, y prime and y prime, another y under a square root sign, and this is 3/2, lots of nonlinearities. So, looking at this, it will be very hard for people to solve it and say that yeah, this is the solution of this, that is y of x is a cycloid. That is what we know is a solution for the Brachistochrone problem. It is difficult to solve, right. Even if you know the solution, you have to substitute it and find out, but you cannot deduce the solution from this, because equation is very non-linear. Okay. That is Euler-Lagrange equation, that dou f by dou y minus d by dx of let me just erase what I wrote, you can see the equation. So, that is dou f by dou y minus d by dx of dou f by dou y prime equal to 0 gives you this equation. Okay. And we have boundary conditions also there. If you look at this equation, it looks formidable to solve. I mean, how do I solve? How do I get y of x? That is our question from here. From here, how do you get there, right? That is where the so called first integrals help you, and you can do that under certain conditions. Let us look at those conditions. Okay. So, to do it analytically, we need to look at a few forms, special forms that enable you to do this analytically by calculating this or computing this first integrals. Okay. These are the special forms for which you can do it easily. Okay. So, there is this first special form where the integrand depends on x and y only, there is no y prime, nothing, just x and y. There is another one which depends on x and y prime only, there is no y, there is x and y prime. There is this third one where we have y and y prime, no x. Okay. The fourth form which has x, y and y prime, all three. Okay. This is no y prime, no y, no x. Okay. Those are the three things. Here a general form where we have a general function f of x y, you can have any function that you like, but y prime has to be in this special form, which is very common in geometry as well as mechanics, because as you know, square root of y prime square basically comes from the arc length ds. Pythagoras theorem says that if I have a curve, if I take this small length here, okay, so that small length is dx and this is dy. So, this is ds, that basically comes to square root of dx square plus dy square, and that basically is what gets you, when you take dx out, you get 1 plus y prime square. Again recall that y prime is dy by dx. Okay. So, these are the four special forms that we are going to consider one by one. The first one is quite easy, right. So, integrand here is only a function of x and y. Euler-Lagrange equations will only have one term, dou f by dou y, there is no y prime, y double prime, nothing. So, you have only this. If you do this, just like capital F, when you take derivative of that with respect to y, you will get another expression or equation only in terms of x and y, that you can solve. Okay. This is more like an algebraic equation, because there is no derivative of y, you have a solution already. okay. And there are no boundary conditions also, because even the simplest boundary condition involved the integrand's dependence on y prime. Since in this case does not depend on y prime, you get a very simple solution here. It may be implicit, does not matter, but you got a solution, okay, an algebraic equation. Now, let us take the case where there is no y, but it depends on x and y prime, okay. In which case if you see there is no y, so when you write Lagrange equations, dou f by dou y is 0, there is no dependence on y, but dou f by dou y prime is present. So, d by dx of dou f by dou y prime equal to 0 is the Lagrange equation. Now, if you integrate on both sides, you get this result, that is dou f by dou y prime equal to a constant c that you can determine from the boundary condition, okay. So, since f depends on x and y prime, dou f by dou y prime will still depend on y prime, then you simply say that y prime equal to some constant, okay. If the dependence on x is not there, it will be constant, otherwise it depend on x and some constant c. You can hope to solve it, because you have y, you can integrate it. On the right hand side there is no y prime, there is only x, then you can integrate and get the solution. So, this is one of the ways of doing it. So, our problem is almost solved here. Now, if you take an integrand of this form where there is y and y prime, there is no x, consider a case where there is no y prime, there is no y, now we are considering a case where there is no x, okay. Then you write Lagrange equations, because both terms exist, because y exists, so dou f by dou y will exist, and y prime exists, so dou f by dou y prime exists, and you have to take this and you get that. So, now we are expanding the second term. So, this term is expanded using chain rule, dou f by dou y, first term remains as it is, this will be dou by dou y of dou f by dou y prime into y prime, like chain rule, okay. And we also get the other term, that dou by dou y prime, because we know that this f depends on y and y prime. So, dou f by dou y prime also depends on y and y prime. We have done y first and then y prime next, okay. Now, this whole equation is multiplied by y prime, because something interesting comes out when you do that. So, basically the previous equation is multiplied by y prime all through. When we do that, the equation that we get can be written or condensed to this form. We are simply multiplying y prime, and in that process what we have on our hand starting from Lagrange equation turns out to be something like this, okay. d by dx of a quantity, that is f minus y prime times f y prime is equal to 0. What does it mean? Then it means this, that is equal to constant, and that is the elegant first integral, that is what is called the first integral. So, when the integrand is of this form, then Lagrange equation you do not have to write and then struggle to solve it. You can simply write that f minus y prime f y prime is equal to constant. That is the solution of the first integral. Again, f y prime in our notation is dou f by dou y prime, okay. That is the first integral. We understand that we have a differentiation at this step, we are getting the solution by integrating rather in a straightforward manner. So, if you look at the Brachiogan problem, that is exactly what it is. It depends on y and y prime. So, for this, instead of struggling with this differential equation, we can go from here to here because of this first integral. So, that is what it means. It may still look formidable, but if you know how a cycloid looks like, then you have a solution here. So, we take that. So, whatever we have that f minus y prime times f y prime, if substitute for this problem, you get a much simpler thing which looks like this, okay, 1 plus y prime square times h minus y equal to constant. It is much easier to solve because it involves now y and y prime in a rather simple fashion, okay, as it is much easier to solve as compared to this. Okay, that is the first integral. Again, first integral is what? F minus y prime into f y prime equal to constant. That is the first integral. There is an insight that you can get from this. For that, let us consider the Hamilton principle for a simple spring massed system that is shown here. Okay. So, here we have Hamilton, or sometimes people call it action, all right, and then what we have inside is actually what we call Lagrangian and so forth, that is why it is denoted as L dt. So, we have this principle. Now, if you want to let me erase this thing and get the pen back. So, this is of the form, if you look at what is in here, there is x here and there is also x dot, okay, just like having y and y prime when independent variable is x, y of x dy by dx. Now, we have time as the independent variable, that is that we have x and x dot, the position and the velocity. Okay. Having noted that, if you look at a problem such as this, we see that we can take advantage of the first integral. Okay. If we do that first integral, which is f minus f y prime and y prime equal to constant, if substitute those symbols in this problem, you will see that kinetic energy plus potential energy is equal to constant. Okay. In other words, what we have is the principle of conservation of energy. Okay. So, when you take all Lagrange equations and get this first integral, that leads to conservation of energy. Okay. That is important thing or insight that comes out of calculus of variations in the first integral, that is you have simplified the problem. Okay. Let us take the fourth form, which is like this: integrand, that f, right, which has a special form, which is y prime appears only like that, x y can appear any which way. Then if you take this already, this is a case of where it depends on y and y prime. It can also depend on x, but slightly things change. The first integral is if you look at this Euler-Lagrange equation, okay, will be slightly different. Okay. Euler-Lagrange equation we have written dou f by dou y minus d by dx of dou f by dou y prime. If you do for this problem, noting this is the integrand, and do a simplification, not simplification, actually expanding the derivative using the fact that it is a chain rule, because it involves y and y prime, because f here contains x and y, right, that is what we have here, all right. So, if you do that, you get more terms and finally you get to a form that looks like that, which is not that easy like the first integral, but it is more systematic. So, you can easily write that without worrying about this square root being underneath and all that, they are gone. Now, you get a much simpler equation to solve. These are the four special forms for which you can get this first integrals or get a solution right away. So, if you try that for a given problem, you may be able to solve it better. Let us take this example. Let us take this as an example where you are minimizing j, which is from x1 to x2 square root of y square plus y prime square. Then the first integral is valid because it depends only on y and y prime. So, we wrote f minus y prime times f y prime equal to some constant. Okay. If we work it out, this simplification, if you do all this, you will get to a form like that. It is still not anything to write home about. no sight of solution yet, we do not know how to solve it, just became a simpler looking equation, but we do not know whether this has an easy solution or not. So, what we do is we try the change of variables. Okay. So, this is a problem where you have to find y of x. So, what we will do is instead of taking x and y, we take u and v. Okay. We had y of x here, but we will take v of u. How do you change the variables? Like this, x equal to u cosine v, y equal to u sine v. When you do that, we have to go back to this equation that we had in terms of x and y, convert them to v and u. In fact, if I write du here, I should actually write u1 to u2, because u has taken the role of x now and v has taken the role of y. Okay. So, now from here we have dx here, that has to convert to du. The way it is dx dv is given by this. When I say xu here, what I mean is that dou x by dou u. Okay. We are changing from xy to uv, but you have to do this Jacobian with all 4 things which are given here, very straightforward. Okay. And du will be replaced with dx will be replaced with du using this, all right. When you do this, you notice that when there is x, x now depends on uv, that is your thing, because we assumed x equal to some function of u and v. In this particular example, we had taken x equal to u cosine v, y equal to u sine v, that is u and v are involved. So, now integrand f, wherever x is there, you will substitute that equivalent thing in terms of u v, and same thing with y, and same thing with this dx. Now, that becomes x u plus x v times v prime, and here we do the same thing. So, we have dx and dy. If this is dx and that is what is here, this is dy. Okay. And that is how the integrand is going to look like. And if you were to write equations, Lagrange equations, instead of f, you have what I can call f1 now, to write down all the things here. We get that, and if you look at this now, we get one equation for v in terms of u, because that is the independent variable now, instead of y in terms of x. Okay. We get this alternate form, and that may be simpler. Why do we do change of variables? Only to make our life simpler. Okay. In this case, this substitution is actually simpler. For that example that we had taken, which is this example, integrand is y square plus y prime square. If I choose a transformation, that is this, which is same as what we have, x and y we had in one way, where I had u and v in terms of x and y. Now, x and y into u and v, if we substitute for all of these 4 things and various expression that we have, this particular thing becomes that, which is y and x becomes u and v. Okay. And that is easy, because it depends only on v prime, no x, no u, no u prime here. So, no v and no u, because whatever we said about integrand being a function of x, y, y prime, now that is equivalent to say f1, I am calling it changed integrand u, v, and when I say u prime, what I mean is du dv by, this is v prime, sorry, this is v prime, is v prime, that is dv by du. okay, that is just like y prime was dy by dx. When we do that, this thing turned out to be a very simple thing, it just happened to be v prime equal to some constant. So, v equal to that and we got the solution. If you substitute that over here, whatever that looked like a formidable equation to solve, its solution, now we have this. Now, from v you go back and say whatever thing is, right, which is x sin y, and on the right hand side we have this C1 u is also here. So, you got the final solution. Okay. So, now we have used two things, we have used the change of variables and the first integral. So, we can use them whenever we have a need. But we must note that given a differential equation that comes from a calculus variation problem, nobody will tell us what change of variables to use. It comes from your own intuition and experience to see when you should use change of variables and how to do the change of variables. Okay, there are some rules, but not general rules that will work for all situations. Okay. Another thing we do is to go for parametric form. Okay. That is, instead of using only change of variables, let us say we try all of that or it does not strike us what change of variables to use, then we go for parametric form. By that what we mean is that we have a problem which has x, y and right. Earlier we changed both x and y in terms of u and v, and we just had different set of symbols u, v and v prime. Now, in parametric form what we do is to express x and y in terms of a third variable called time or t. Then probably you will say time, but that is there. Okay. Now, in the parametric form when you do it, whatever integrand you had in terms of x, y and y prime, it will become x of t, y of t and x dot by y dot. What you want is y prime, right. So, y prime is dy by dx, but you want to divide and multiply by t, dy by dt divided by dx by dt. Okay. That is what we have. In fact, it should be other way around. This should be y dot by x dot, because that is dy by dx. We are just doing the time. So, just make that correction over there. Now, instead of that being f, now it will be a different function, because when you substitute, expressions do change, you have a different expression side, and on that we say that the Lagrange equations are satisfied. This can be proven or checked against, not a major result. Say that whatever integrand f that you have now converted to psi, that can solve these two equations. Okay. When these equations are solved, you get the solution for that x of t, y of t. See, note that you have two unknown functions opposed to one unknown function. The change parametric form, instead of y of x being unknown, you have x of t and y of t as unknowns. Accordingly, you get two differential equations. Okay. So, here is a comment that this parametric form is usually quite useful in many situations, especially when y of x is to denote a closed curve, right. For example, if I have a problem like this where I have to find y of x, we always think that y of x in open curve. So, at one point there will not be two things, but optimal design or geometry problems also, when you have closed curves, it is not a function really. If this is x and this is y of x, for the same value of x there are two values of y. Okay. In those cases parametric form helps, so that now you can go around the curve with a parameter t, which will go to t equal to 0 to all the way L. Okay. Having discussed this, we will go to a more important concept of Noether's theorem in the next half of the lecture. Thank you.